Okay, we're on to number 14. We have a graph showing the net force on a 5.0 kilogram object over time. And the first part of this is, what quantity can we compute from this graph? So we have force over time. We know what the force is over a period of time. All right, so constant force, we use F equals ma. We don't have that here. The force clearly grows, then is constant for a bit, then dies down, but it's not constant the whole time. So there's momentum approaches, and there's energy approach. Energy approach is, that's based on work, which is force over a distance. So if this graph were force over, like x, over position, that would be work. In the momentum approach, right, the impulse is force over a period of time. That's literally what we have a picture of here, right? Force, what the force is over a period of time. And so it's the momentum approach that we're talking about, and in particular, we can compute the impulse here. We can like total up the amount of force over the period of time here. So it's impulse, force over time. Again, work, it would have been work if this were x measured in meters. That would have been work that we could compute, but it's impulse. So the impulse, it's force times time, but in a case where the force is not constant, it's the integral of force dt, d time. But of course with a graph, we can do it using the area. So B asks us to figure out what the quantity is, so we need the area under this graph. So the impulse sort of officially is force dt, but from a graphical point of view, it's the area under the graph. Okay, so a little bit of geometry here. We're going to have a rectangle and two triangles. We're going to have, so for the two triangles, we're going to have 1/2 times the base, which is 1 second, times the height, which is 10 newtons. Okay. Then the rectangle, so that'll just be length times width, so that'll be a 3 second width times 10 newton length, or height. And then the triangle on the right, 1/2 times, we've got 3 seconds for the base, and we've got again 10 newtons for the height. So we got, what's that, 5 newton seconds plus 30 newton seconds plus 15 newton seconds, which is 50 newton seconds. So that's the impulse, 50 newton seconds. Okay. Question C is, if the object starts at rest, how fast is it going after this force has been applied? Yeah, so impulse is change in momentum, right? This is definitely a momentum approach type problem. So the change in momentum is the impulse. It's the 50 newton seconds. So the momentum will go up by 50 newton seconds. If this was meters, if this was x in meters, we would have computed the work, and then the work would have been how much the kinetic energy would have changed, assuming it was just horizontal and there was no potential energy involved. It would have been how much the kinetic energy changed. It would have been delta k in the energy approach. But with impulse, it's delta p. It's the change in the momentum. Okay. So the momentum changes by 50 newton seconds. But we know that it started at rest, so it had 0 momentum to begin with, so the final momentum must be 50 newton seconds. And that's m times Vf is 50 newton seconds, so we divide by m, which was 5 kilograms, so that's 10 meters per second. So the object will be going 10 meters per second after this impulse. Okay. Final problem, number 15. A 1.2 kilogram block rests on a frictionless surface next to a spring with spring constant 75 newtons per meter. The block is pushed against the spring so that it is compressed by 0.30 meters and then let go. So how fast is the block going when it slides away from the spring? All right. So we have a spring, and spring forces are not constant. So F equals, although we could figure out what the force from the spring is here, right? As soon as it starts pushing back, as soon as we let go and this thing starts expanding and pushing the block, that force is different that whole time between here and here as the object gets pushed. It's not a constant force. So F equals ma is not going to be fruitful here. It's going to be too hard. But the spring is a conservative force, which means it lends itself very nicely to the energy approach. And in fact, it's because it's a conservative force, right? We can put the block and the spring together as a system, and this is an isolated system. And again, because the internal force is the spring, which is conservative, so we actually have conservation of mechanical energy here. So the amount of mechanical energy in this picture has to equal the amount of mechanical energy in this picture. So we can do a Ki plus Ui equals Kf plus Uf kind of equation. Now, initially, in this picture, right, the object is at rest. It's got no kinetic energy. It's all spring potential energy right there. It's all, so it's 1/2 K initial x squared. That's the formula for potential energy of a spring. Okay. Now the spring pushes, this thing goes flying away. After it's flying away, it's no longer touching the spring. It's got no potential energy. And of course, it's not going up or down, so it also doesn't have any gravitational potential energy in this problem, at least not yet, until part B. It's all kinetic energy. All that energy that was stored up in the coiling of the spring here now is all in the speed of the object here. And that's 1/2 mvf squared. Okay, so we have K, we have the initial position of 0.30 meters, we have the mass of the object, and we're looking for the speed of, we're looking for VF. So you do some algebra, we can cancel the 1/2, divide by m, take the square root. I can put the whole thing under square root, or since it's xi squared, I can just take the square root of the xi squared and call it xi outside of the square root. However you want to do that algebraically, just make sure you're consistent. Okay, and so there's my expression for VF. And then I put in my numbers, which looks like that. And I think that comes out to be 2.4 meters per second. So this object will be going 2.4 meters per second because all that potential energy got turned into kinetic energy, and we knew how much. Okay. Finally, part B is now continuing this problem. This object keeps sliding at this speed and then encounters an incline. So here's the picture. So the object's moving along, and it starts going up the incline, and it gets to a certain height, and of course now it's going to come to a stop. And the question is, how high up does it go? Call that YF. Okay, so again, we can think of the object, the block, and the Earth together. That's our system. Gravity's going to matter here. So including the Earth means gravity is going to be an internal force, but it is conservative. There are no other forces that involve with energy, so this is isolated. So again, we have conservation of mechanical energy. We can say Ki plus Ui equals Kf plus Uf. In the beginning, which is actually, it was the final picture up in part A, it's now the initial picture here, right? We have no potential energy. We're at ground level, so no gravitational potential energy, and the spring is behind us. And then in the final picture, we go up a height, so we will have potential energy. It'll be gravitational potential energy now, but it'll come to a stop. We're looking at the moment when it comes to a stop, and so that means it'll have no kinetic energy. So it's the initial kinetic equals the final gravitational. So 1/2 mvi squared equals, and now we have to use the gravitational potential energy formula, mgyf. and that will allow us to solve for yf. All right, the m's cancel, so actually for this part the mass doesn't matter. I'm going to divide by g, so I've got yf equals, I've got the vi squared, I've got 1/2, so that's in the denominator, and I'm dividing by g. So vi squared divided by 2g. I plug in the numbers, and I get a final answer of 0.29 meters. So that's how high up it goes. Let me just say that that's not how far it actually traveled. That depends on how steep this incline is, right? So if this was a not very steep, just a few degrees, then it would actually travel for a while until it got this far off the ground. If it was really steep, it wouldn't travel very far because it would be able to go up the 0.29 meters really fast. It would just go zoop and then probably fall back down. So yeah, so this is just literally the vertical distance, which we can know without even knowing the angle. Okay. But I think the main thing in this problem was realizing that it was a conservation of mechanical energy type problem. I suppose that, well, no, I was going to say that you could have used F equals ma in this section. Not that you would want to, it would have been a lot harder, but actually I don't think you could have anyway because you don't have the angle here. So, you know, figuring out how gravity splits up between horizontal and vertical once you start going up, you would need that angle, and you don't have it. So you actually kind of had to do the energy approach here. Okay, so that's the final problem in the test. And I hope that these solutions helped you understand how these problems worked.